last Friday, we were talking about limits and continuity, right? And I forget, help me remember, I think I just commented all the same theorems about how limits for complex value functions behave in regard to sums and products is the same as for real value functions. Did we actually write that down, or did I just say that?
I think you just said it.
Okay, yeah.
You have some definition and a few examples in this.
Right. Okay. So did I give us the definition of continuity?
No.
Oh, okay. Great. And we'll just start there. Okay. So. Definition is a function complex, of course. The setting that we're confining ourselves to is a function defined in a neighborhood of D naught. Then F is continuous at Z naught. If we have the limit expression as Z goes to Z naught, so F is equal to F of Z naught, the function value at the point Z naught. And so this type of machinery that we built, a limit, is how we define continuity, right? Just as in the case of real value functions, we may have it that our function f is defined by some formula at points not equal to z naught, and then has some specific chosen value at z naught. This would be an example of where our function may not be continuous, right? Because that is to say, we can approach z naught in some way so that the values of our function are given by some formula for f, and then we could pick any old random complex number to be the value of f at z naught. But when this limit and this function value coincide, that's our definition of continuity. And you'll remember this hopefully from Calculus 1. Formally, it's exactly the same. The underlying difference here, something that we've touched on a few times, is that there are infinitely many ways for z to approach z naught, right? Whereas in the case of a real number, there's only two directions you can come from. Right? And that's actually going to end up being the main difficulty in extending our standard definitions from the calculus of real functions to the calculus of complex functions. Here it's no different, really. There's no extra difficulty involved quite yet. But the point is that when we're taking the limits over complex numbers, that has a slightly different connotation. Okay? So, I think it's probably obvious how to extend this. That is to say, f is said to be continuous in a subset S of its domain. If it is continuous at point of S. Okay. A pointwise condition. Okay. So I'll tell you a couple of theorems that I anticipate are familiar about limits of real functions that just carry over without any difficulty to limits of complex functions. We're not going to prove these things, but I should have them written down just so you remember the things that you can do to manipulate limits. Okay, so first we'll assume if the limit z approaches z naught of f of z is equal to a, and the limit as z approaches z naught of g of z is equal to b, for complex functions, f and g then well, if we take the limit of the sum or difference of these functions, we just get the sum or difference of these values a and b that we suppose that our limits converge to. Okay. Same type of assertion if we consider the product of these functions. And furthermore, we can consider a quotient and get a very similar result. But here, of course, we have to say when the complex number that g converges to happens to not be 0. Okay? So an immediate consequence of this is that if f and g are continuous at z naught, then so our f of z plus or minus f of g, the product and the quotient continues at z naught. For that last one, of course, as long as g of z naught is not equal to 0. Okay, so the point of all this is that we can construct new continuous functions from old continuous functions by taking their sums, difference, product, quotients, and also, as a matter of fact, their compositions. Just like we could do with real functions. Yes?
Because like you can approach z naught from like infinitely many sides, is there no analogous squeeze theorem in complex variables, or is there some sort of Because like I know in real analysis, we just kind of beat squeeze theorem to death. And like I know it's really important in
Yeah.
real numbers, but obviously that's the two sides. Is there any sort of analogous theorem in complex variables?
So you can formulate something weaker but analogous, but we won't really use it.
Yeah, I was gonna say I don't really see it having any sort of use.
Yeah. So that's a good question. Try to think about how we would even say an analogous statement for a function, a complex function. But yeah, we won't really talk about it because it's not that useful to us.
Yeah. Thank you.
Good question. Okay, so right away, what this tells us is that polynomials of a complex variable are continuous functions, right? So, polynomials, that is functions of a complex variable of the form an times z to the n an minus 1 times z to the n minus 1 a1 times z plus a naught I guess I should use the index j, are all complex numbers, continues. Everywhere, I should say. Okay. And rational functions. What do I mean by rational functions? I just mean ratios of polynomials for example, r of z is equal to an times z to the n, a1 times z, a naught, divided by b sub m times b to the n, I'm sorry, m, all the way down to b1 times z plus b naught. Of course, again, I have a sub j and b sub k, all complex numbers, for j between 1 and n, and k between 1 and m, are continuous where the denominator is non-zero. Okay. That is to say, we exclude the points, the zeros of this polynomial in the denominator from the domain of definition. Right? Our function r of z will be undefined at any point where the denominator is 0. Okay? So, the takeaway from this, so, compute limits of continuous functions. Just plug in, just like we're familiar with doing. So a couple quick examples. Let's let f of g be the rational function given by z plus 2 times I divided by z. And if I ask you to calculate the limit at z approaches 2I of this function, what do I get? Well, undefined here. So yeah, I just get 2. I can plug in 2I into the value of z. Okay, so I just get 2I plus 2I divided by 2I, which is 2. Well, okay. Well, instead, if I set g of z equal to the rational function z squared plus 4 minus z squared minus 2I times z. Okay? And I'll ask you to find the limit as z approaches 2I of g of z. Okay. So, first of all, what's my domain of definition for g? Yeah.
Everything except 0 and 2I.
Yeah, it's everything except 0 and 2I. How do I know that? I set the denominator equal to 0 and see what values of z make that equal to 0, right? So I factor z out here, right? And I get z times z minus 2I. So the two values of z are just 0 and 2I. Okay? So g of z as domain of definition c minus the 2 points 0 and 2I. Okay? But notice, not only can I factor the denominator, I can also factor the numerator. Right? How do I factor the numerator?
Z minus 2I, Z plus 2I?
Yeah. Remember, I quoted you a theorem on the first day of class that every polynomial with complex coefficients of degree n has n solutions. What that means is that you can always write a polynomial as a product of n factors, z minus omega 1 times z minus omega 2 times z minus omega 3 up through omega n. You can factor it into linear factors. That's what that's saying. Every polynomial splits into linear factors. You can always factor all the way out. Okay, we'll prove that next week. Not to quote that too much before we actually say anything about why it's actually true, but here's an instance of that. In any case, we cancel these two factors, right? Z minus 2I and Z minus 2I appear both in the numerator and the denominator. So what we get is this function. Now, this looks exactly like f, right? But remember, it takes more than just a formula to specify a function. We have to say what its domain is. The domain of definition of g is this. Even though we don't have a factor of z minus 2I in the denominator any longer, our function is still not defined there. Okay? Whereas the domain of definition of f in our previous example was just the set of all complex numbers except for 2I. or except for 0, sorry. Okay? So, that's okay though. Remember, when we compute a limit, we don't need the function to be defined at the point we're trying to compute the limit. We just need it to be defined for everything up to this number that it may not be defined for. And then we have to check this epsilon delta condition. Okay, so what this amounts to is that the limit as z approaches to I of g of z is actually just the same as the limit approaches to I of f of z, right? That is to say, despite not having the same domain, since we can arrive at the same formula, we can evaluate the limit by just taking the limit of f, right? Which of course just gives us the same answer as before. Okay, so here we say g of z has a removable discontinuity. And z equals to I. What do I mean by that? What I mean is that even though g of z is discontinuous, that is to say, it's not defined even at z equals 2I. Can't be continuous if you're not defined in place. Right? We can restore continuity by simply defining a new function, g star. Okay? Define g star of z as just g of z for z in the original domain of g, right? Complex numbers minus 0 and 2i. And define it to be 2 just for the single value z equals 2i. Okay? So because the limit exists and is equal to 2, and our original function g is not defined at 2i, we can simply define a new function which is defined as 2i as the limit of g as z approaches 2i. We've removed the discontinuity at 2i. Okay? Okay. So. Okay, just take a second to reflect here. When we discussed taking the limit of a sequence of complex numbers, and then talked about taking limits of functions. We insisted that our functions be defined in some open neighborhood of a point we wanted to take a limit at. Right? So this is illustrative of what's going on and why we say that, why we have to make that allowance. Because the limit as g of z approaches, as z approaches 2i, is defined. It makes sense. You can say that the value of that function is getting closer to 2, but the function itself is not defined at that point. Okay? So, just a final note on all this limit business. Note. And also, sets of limits involving infinity, by working in the extended complex numbers. That is to say, the limit as n approaches infinity of some sequence of complex numbers z sub n is equal to infinity if for all positive m, no matter how large. Okay, I write this for emphasis because remember we're talking about positive epsilons and positive deltas, and we were thinking of them as getting smaller and smaller and smaller. Now I'm saying take an arbitrarily large positive real number m. There is an int capital N so that the modulus of z sub little n is strictly greater than big M for all little n greater than big M. Right? So this is saying for any arbitrarily large positive positive real number m, we can choose a point in our sequence such that everything that comes after that point will have a modulus larger than m. And that choice of point in our sequence, z sub n, is this capital N. Every term of the sequence that comes after that will have a modulus larger than m, is what I'm saying, is how we define the limit of the sequence z sub n going to infinity. After a certain point, we don't get any smaller than a given cutoff in modulus. Capital N. Okay. All right. So similarly, the limit as z approaches z naught f of z equals infinity if a very similar condition here, if for the positive real number capital M, there is delta greater than 0 such that the modulus of f of z strictly greater than capital M whenever we have the following: the modulus of z minus z naught is between 0 and delta. Okay, so let's take 1 second to unpack this. What am I saying here? I'm saying that I can choose choose a small neighborhood around Z naught so that I can make my function value as large as I possibly want. Right? That is to say, whenever I'm inside this disk of radius delta centered at Z naught, I can ensure that the modulus of my output inside that disk is larger than an arbitrarily large positive real number, m. Okay? Okay. Right. So, all that being said, now we can start to address where things really become sort of counterintuitively complicated. Everything we've done here so far over the past, the end of Friday and everything we've done today up to now is a fairly straightforward generalization from the theory of functions of a real variable. Okay. So now we're going to start to dip our toes into differentiability. And this is where the infinitude of directions in which a sequence of real complex numbers can converge to something really kind of screws us up. We have to be really careful about what we do in regard to the definition of the derivative. Okay, so we're going to start to talk about analytic functions. Okay, so here's kind of a historical perspective on how we arrive at this definition. So far, we've just defined a complex function to just be specified by two real value functions of two variables, right? Which is not all that restrictive. Let's take, for example, let me just say, a complex function so far is specified by two real functions u and v of two variables each. But let's quickly look at two examples of such a construction that are fundamentally different in character. Okay? So I'll ask you to consider the two real valued functions of two real variables, u1 x comma y given by x squared minus y squared, and v1 of x comma y given by 2xy. And then consider a second example, a seemingly quite similar situation. I'll take u2 to be just the same function as u1. And this time I'll take v2 to be a slightly modified version of v1, just 3 times xy. How are these different? These are all nice formulae, right? We just kind of talked about how polynomials are in general pretty nice. You know, at least they're continuous, but there's an important distinction between these two. Yeah.
Is it a matter of factorability?
Factorability. What do you mean by factorability exactly?
So I'm not quite seeing it yet, but like you could write u or u1 and v1, x squared minus 2xy minus y squared can be factored to x plus y, x minus y. But the for v2, the extra like multiple of xy means you can perfectly factor it.
Okay, this is a good thought. There's something to that. Well, let me tell you something. So let's note f1 of z given by u1 of x comma y plus I times v1 of x comma y, where we follow our usual notational convention.
So is it x plus y squared? Or, sorry, x plus iy squared, the first one?
So this function f1 can be expressed as just z squared, right? So you're definitely onto something with factoring, right? So what happens when I square this complex number? It's in terms of its components. I get x squared plus 2i xy minus y squared. Or, broken up into real and imaginary parts, what do I get? I get x squared minus y squared plus I times 2xy. So, what my claim is that I've just demonstrated to you that the function f1 specified by these two real functions of two real variables can be expressed as just operations on z alone. I don't have to break it up into taking the real and imaginary parts of z to define what the function f1 does. I can do that, but that just falls out of some manipulation I did to z as a number in its own right. Okay, so I claim that f2 defined by the functions u2 and v2 cannot be expressed this way. And we'll prove that later today. But for now, let's just take my temporary word for it, that that's the difference between these two functions, f1 and f2 of a complex variable. The f1 can just be expressed in terms of operations just on z. That is to say, difference between F1 and F2 is that 1 treats Z as just a number. Okay, so that is to say, you think back, we take a function from a real number to a real number, and we evaluate a function f is, let's say, 5 plus 3 root 2, right? Remember when we were constructing larger and larger number systems? We're not concerned with functions of a real variable that just take this and return 3, the coefficient on root 2, right? When we study real valued functions, the fact that we can write a potential input of this form does not give us the license to be like, okay, let's just express all real numbers of this form and take their parts separately. That is to say, our real functions don't rely on some arbitrary choice of how to split up a number. So this is what we want to do in restricting the complex functions that we pay attention to. Okay, now the way I've described it here, it seems like, how could we give an effective description of this condition? Right? And by effective, I mean something that we could write in a formula, or given an arbitrary formula for a complex valued function that incorporates the real and imaginary parts. How can we tell if it only treats Z as a number in its own right? Because, I mean, we have formulae for real and imaginary parts in terms of Z and its conjugate. So that's something we can do, kind of fiddle around with the arithmetic and algebra. But we would like something effective, by which I mean something that you could feed into a computer. I kind of check, have the computer check if a function is like f1, even though originally expressed in terms of the real and imaginary components, can be resolved into just operations you can do on the complex number as a number in its own right. Okay. Okay. So okay, let's make some preliminary observations. So, for example, functions like the identity function is allowed. Obviously, what I just told you, the square function can be expressed as just something you do to Z on its own. Similarly, any higher power, for example, x cubed, should be allowed, or we should consider this function as admissible. then, in fact, we want to consider most powers. For example, 1 over z, the inversion mapping. Which, of course, I'm giving you the expression in terms of the real variables as well, just to give you some preliminary view of what these functions that we're admitting into consideration look like. Okay, so we want all these functions to be admissible. Okay, not like F2. And again, I said we'll prove that F2 is not of this form later today, but here's some functions which are clearly not like F2. Or sorry, that are like F2 that we don't want to consider. So we just take the real part of z, well, that's not of this form, right? We're taking some component of z separately. Likewise, the imaginary part, okay? So here's maybe a kind of surprising one. We don't want complex conjugation to be in the admissible set of functions. Why is this?
It modifies all the imaginary components.
Yeah, or you could say it modifies both the real and imaginary components, right? You can express it in terms of either one. But the point is that you can write a formula that, that there's no, this conjugate always depends on either one of real or imaginary. Not both at the same time, in a way that it's just a single operation on z. Okay? So yeah, this is to say, this is, for example, equal to 2 times the real part of z minus z. Okay? Remember the formula for the real part of z? But no, you're right. This is what you said is a fine way to think of it. It's just switching the sign on one of the components of z, right? That's treating the components separately. But also, we just disallowed the real part of z, and this is expressible as just an operation on z. We're just negating the whole thing. But we're still taking an individual component. So a kind of geometric way, and here's an algebraic way of seeing why we shouldn't allow conjugation. Okay. One more. Neither should the modulus of z be allowed, right? Because this is just the conjugate of z divided by z, take the square root of that. Okay? So, right. So, right. Check. It is consistent with not allowing the function f2 that we described at the beginning of this session. Let's do this together? No. So, right. What do we get here? We get f2 of z is equal to x squared minus y squared I times 3xy. So here we're going to do this the laborious way, right? Remember, x is just z plus z bar over 2, and y is z minus z bar over 2I. Okay, so plug this in. What do we get? We get z minus z bar over 2 squared minus, oh sorry, there's a plus. Z minus z bar over 2I squared. Plus I times 3 times z plus z bar over 2 times z minus z bar over 2I. Okay. If I simplify all this, oh sorry, I forgot a parenthesis here. If I simplify all this, what do I get? I get 5/4 z squared minus 1/4 z bar squared. So I have one summand which treats z as a number, and then I have one summand which includes something that we agreed should be disallowed, conjugation. So that means our function 2, f2 altogether, should be disallowed. Okay? Is inadmissible. As originally claimed. Okay. So, let me ask you to do a couple more of these. Yeah.
Could you also write F2 as z squared plus 2 real part of z, imaginary part of z? Or sorry, 1 real part of z. What we have for F1 plus just real time real z, imaginary z. And
Yeah.
both of those are inadmissible.
Yeah. That's also fine. Anything that you can. So, yeah. This is just this isn't a proof yet, right? This is just showing you it's like, oh, it does have some inadmissible part, right? I haven't proven to you that you can't write it as just some operations on Z alone, but you may get a feeling like you can't just seeing this. Okay, so yeah, you can get a similar feeling from having it written as something with a summand that has an inadmissible function. Yeah, this is important. This is not a proof that I just gave you. This is at least consistent with what we have written down so far. Okay. Okay. So, right. So. Determine if the following are admissible. h of z equal to x minus 1 minus I times y, all divided by x minus 1 squared plus y squared. Okay. So let's just think about this for a minute, and then we'll discuss together. I realize this is a little heavy on the algebra, but any thoughts? Is this admissible, or do you think perhaps it's not? Can we express it in terms of just operations on z? How about this? Why don't I ask you, what are the first few steps we should take in trying to
Factor the denominator.
factor the denominator? Okay, so how do we propose to do that?
It's like a difference of two squares. Except it's a sum, but we just put an I in there.
So you just want to put an I in it somewhere. Is that the claim?
Once we factor it, there will be like an I times y.
Right. That may help. There may be a way to go around with that, but I think you actually get more simplification by going a different way. And yeah,
So I think we're allowed to add and multiply by functions on this list, right?
yeah. So if you can express this function h as some addition or multiplication of functions on this list, or inversion, yeah.
Inversion. So what I did is to write the function in terms of z and y.
Z and y.
Yeah.
Okay.
And then you get some fraction, and you can invert it a couple times, and then basically separate out the part that only depends on y, which shows that it's not admissible.
Shows that it's not admissible. So remember, again, this is not a proof that this is inadmissible. So coming up with an expression that is inadmissible for a function does not prove that it's inadmissible. Okay, I'm still claiming this. So let me tell you outright that this is admissible. Now let's see why. Okay, so I'm just going to use the fact that x is the real part of z and y is the imaginary part of z, and use my formulae involving z and z conjugate for the real and imaginary parts of z. Yeah. So this gives me z plus z bar over 2 minus 1 minus I times z minus z bar over 2I divided by z plus z bar, over 2 minus 1 squared plus z minus z bar over 2I squared.
For the numerator, you could just like swap the places of the -1 and the minus iy and just say that like x minus iy is z bar and then -1. Right?
Say that again. Sorry.
So like in the numerator, the x minus iy is just z bar, right? And you just have -1 afterwards. You just
Yeah, you could just say z bar there. Yeah,
Okay.
that's even faster.
okay.
Yeah, that's great. That's a time saving trick for sure. That's good. And we get the same thing by doing this, right? We cancel our i's, and then minus z plus z. Z's cancel, and we get z bar over 2 minus negative z bar over 2. Z bar minus 1. Okay. So we get z bar minus 1 in the numerator. Okay, and how about in the denominator? What do we get? We get z plus z bar squared over 4 minus z plus z bar plus 1. Right, all I did was square this binomial. Okay, and then I get plus 1. 1 plus z minus z bar squared over 4 So, what does this give me? If I simplify my denominator now, I get z bar minus 1 divided by z times z bar minus z minus z bar plus 1, which I can just factor z bar minus 1 times z minus 1. 1 over z minus 1. Yeah.
Should that be a minus sign in the bottom right of
Yeah, when you square the
squaring?
Oh, you're right. I'm sorry. Yeah, I wrote that in my notes too. Good, thank you. Which actually makes my simplification valid. Otherwise, what I wrote was wrong, right? Okay. So, as you can tell, this is really hard to tell in general. Okay, so again, we really want to come up with some effective criterion to do this. Or else we're just kind of like making substitutions and doing algebra until we can arrive at something, possibly arrive at something that has just operations on Z. Okay, let's look at one other thing. This is kind of a joke. Let's look at G of Z. Yeah. Okay, Z times Z bar squared plus Z squared plus Z bar squared minus 2Z bar Z squared minus 2Z bar plus 1 divided by 10Z bar plus Z bar squared minus 2Z Z bar minus 5Z bar squared plus Z minus 5. Okay, how do we tell if this is admissible or not? I guess I should write the conclusion here. Well, I don't expect you to come up with this. This is like kind of stupid. Has a factor of Z bar minus 1 squared in numerator and denominator. And canceling makes it admissible. Okay, the only reason I write this down is because there's, using the method that we've outlined to determine admissibility so far, there's in general no hope of doing this in a reasonable amount of time, you know? So, let me just point out another example before we move on that seems kind of counterintuitive. Let's take f of z equals to e to the z. So remember, we defined this as e to the x times cosine y plus I sine z. I'm sorry, y. Okay, so that is to say, we've separated out the real part and the imaginary part of z. The standard expression that we use may suggest that e to the z is inadmissible. But wait, hold on. We also mentioned that in the power series development, we have this identity, right? And on the right here, we have only operations in treating z as a number, right? So, secondly, e to the z is a nice function. We would like it to be admissible, but we still have to make sense of, well, what are we really looking for here? What is the right way to describe this condition of admissibility? And the answer is that, does anybody have a guess what it is that makes a function admissible or not? I don't blame you, it's not clear at all from the examples we've looked at. But it's differentiability. If a complex function is differentiable, it's admissible. Okay? And under mild conditions, you can say the other direction as well. Admissibility defines, with a little bit of extra condition, implies differentiability. Okay? And this is the gateway to talking about analyticity, which is a slightly stronger condition than differentiability, but it hinges on differentiability. Okay, so an effective condition for this thing we've been calling admissibility, ability. Is ability. Okay, so let's define what it means for a complex function to be differentiable. Okay, so f a complex function defined in a neighborhood of Z naught. Then the derivative of f at Z naught is given by df dz evaluated at Z naught, or again, using the familiar notation of calculus 1, f prime of Z naught is just equal to the limit as delta z goes to 0 of the function f evaluated at Z naught plus delta z minus f of Z naught divided by delta z. Provided that the limit exists. Okay, so again, this is exactly analogous to the definition of differentiability for a function of a real variable. The primary difference being that there are infinitely many ways for delta z to approach 0. Delta z is some complex number, right? Think of it as a difference of complex numbers, which is obviously a complex number. And for all the infinite variety of ways that delta z can approach 0, we must have that the limit tend to the unique complex number f prime of z, independently of how delta z approaches 0. Okay? Note, no matter how delta z approaches 0, we must have a unique f prime of z naught or limit to exist. In reality, we dealt with this same problem in Calculus 1 when we talked about left and right hand limits. We have to make sure that the left and right hand limit agree so that the limit agrees. But now left and right handed are replaced with an infinite number of ways you can approach 0. Okay? Okay, so let me now prove to you that we were justified in excluding z bar from the admissible functions by showing you that the function f of z equals z bar is not differentiable anywhere. It is differentiable nowhere. Okay? F of z, the function given by z bar, is differentiable nowhere. Okay. So, let's just look at the expression inside the limit for the derivative, the difference quotient. Okay, so f of z naught minus delta z, plus delta z minus f of z naught divided by delta z is just by the definition of f, conjugate of z naught plus delta z minus conjugate of z naught over delta z. So remember, the conjugate splits across sums of complex numbers. Yeah, so really what we get here is just conjugate of delta z divided by delta z. Okay, so let's say, let's suppose first delta z approaches 0 in a way parallel to the real axis. And let me draw you a picture. Here's my point, Z naught. And let's say my delta Z is approaching 0 just along this line parallel to the x-axis. So that is to say, my imaginary component is fixed. Right? So when I take the difference of this endpoint in Z naught, I'm just changing in the x direction. Right? My delta Z just becomes delta x. Yeah. Okay? Then delta Z is just delta x, which implies that the, in this case, the conjugate of delta Z is just delta Z itself, since delta Z is just real. Yeah? Okay. Okay. So the limit as delta Z approaches 0 of the conjugate of delta Z over delta Z is just 1. Right? They're decreasing at the same rate. Okay, so on the other hand, let's assume if delta Z goes to 0 parallel to the imaginary axis, what do we got here? Same type of picture. Get delta Z here. I guess I can add to this. In this case, I just get delta x, right? What do I get? In this case, well here, since I'm parallel to the imaginary axis, I have the fixed value x naught, or all complex numbers along this line, right? So when I take the difference, when I take delta Z, what do I get? I just get
Delta y.
I get I delta y, right? Because delta Z is a complex number. I still have that I in there, but yeah, conceptually, the right idea. I delta y. I get delta Z is just I times delta y. Okay? Which implies that along this direction, the limit as delta Z goes to 0 of the general expression I derived, conjugate of delta Z divided by delta Z, is just the limit as delta Z goes to 0 of I delta y, I, delta y, sorry, negative, yeah. Again, I get these quantities are equal, and there's a negative 1 left, constant in my limit, so I get negative 1, right? Okay. So, the limit in question not be assigned a unique value. So, this function, conjugate of z, is differentiable nowhere. Okay, that is to say, my point z naught was arbitrary, right? I showed that conjugate z is not differentiable at an arbitrary point z naught. So that is to say, it's differentiable nowhere. Okay. So,
What if the imaginary part is 0?
what if the imaginary part of what was 0?
Z is 0.
Z naught.
Of z naught is 0?
Z naught.
That's fine. We would just happen to be on the x and y axes in this argument. Right? That is to say, my complex number delta z, when approaching from a path that's parallel to the z axis, real axis, would actually be on the real axis. Right? The same thing for if I was just at the origin, if z naught was at the origin. Then-
Well, in that case, like, the conjugate of delta z would be equal to delta z.
when we're approaching from a parallel to the real axis, which is exactly what we used here. The conjugate of delta z is delta z. Whereas when we deduce this, our conjugate changes sign. And that's exactly what I almost forgot to write here. You get this negative 1. And that's why you get conflicting values for the limit, depending on how you approach your point, z naught. Yeah.
I'm just trying to apply this to the real numbers, where I just take the real axis as the only, like, valid axis.
Yeah. So then it becomes just guaranteeing that the left hand and right hand limit are the same. So it's having this perpendicular axis, which is affected by what conjugation does, that gives us this. Right, so
Yeah, okay.
in the real numbers, conjugation is just the identity function, right? So if we were to restrict ourselves to real numbers, then conjugation is, that is to say, yeah, I see what you mean now. If you're on the x-axis, these two ways of approaching will agree, but any other way won't, right?
But then the real numbers left are the only one that actually matters.
Exactly. They're the only thing that actually exists. Yeah, good. Is that okay with everybody? Good question. Okay. So, let me just really quickly tell you what you probably guess is true already. Differentiability, it's subtler, but it behaves formally just like differentiability for real functions. Let's say if f and g are differentiable, I should say at z, the derivative of plus or minus g at z, is equal to the derivative of f at z plus the derivative of g at z. 2, we can pull constants out of derivatives. The derivative of c times f at z is equal to c times the derivative of f at z for c any complex number. Thirdly, we get the product rule. The derivative of f times g evaluated at z is equal to f evaluated at z times the derivative of g evaluated at z plus the derivative of f evaluated at z times g evaluated at z, just like for real functions. Similarly, we get the quotient rule. The derivative of f divided by g evaluated at z is equal to g evaluated at z times the derivative of f evaluated at z minus f evaluated at z times the derivative of g evaluated at z, all divided by g squared evaluated at z. And finally, the chain rule. If f differentiable at g of z, the derivative of f of g of z is equal to f prime of g of z times g prime of z. Okay, just completely analogous to the basic rules that you knew from Calculus 1. Okay, so again, polynomials and rational functions, super nice, right? Polynomials are differentiable everywhere, and rational functions are differentiable everywhere in their domain of definition. Just like we said they were continuous, same story here. We can build them up using these rules of differentiation, right? Okay. Here's our key definition. What we're actually going to spend most of the rest of the term talking about. A complex value function f is said to be analytic on an open set G if f has derivative at every point
of G.
So this is saying f is differentiable at all points in G.
Yep. Having derivative is differentiable. Those are synonymous. But note here that analyticity is defined in terms of an open set. Okay? Differentiability is a pointwise condition. Analyticity can only be defined on an open set. Okay? It's a stronger condition. That is, if you're, to say you're analytic at a point means that you're differentiable at infinitely many points right near that point. Okay, and we'll actually use that as shorthand quite often. We'll say analytic at a point Z naught. What we mean by that is that there's an open neighborhood around Z naught for which f is analytic. That is to say, it's differentiable at every point of an open neighborhood around Z naught. Okay. So, yeah, I should say that. Sometimes, by which I mean often. We'll say f is analytic at Z naught to mean f is analytic on some open set containing Z naught. So in quotations is what we'll say often, but what we actually mean is underlined here. And that's just for convenience. Just keep in mind always that analyticity is defined for open sets, not just points.
So is it not generally going to matter what the open set is?
That depends on the situation that we're trying to analyze.
So if we're saying like f is analytic at Z naught, it's because we don't really care what the specific open set is, just that there exists one.
Yeah, so really, again, it's a stronger condition than differentiability because we're saying that the function behaves nicely, is differentiable necessarily somewhere around this point. It doesn't always matter exactly what that set is, but for some occasions we may want to specify the particular largest set we can. So yeah, that'll come problem by problem as to where we make that distinction. But yeah, in general, we don't care what the open set is. If we say it's analytic at a point, we just know that we can do some nice stuff in that open set. Okay, yeah, that's our time for today. I meant to ask at the beginning of the class, but I forgot. How's the problem set going? It's going.
It's difficult.
It's difficult. Okay. Okay. Is it too difficult?
No.
I guess we'll find out.
Is there like an expected time that it should take?
No, I don't think it would be fair for me to say an expected time that it should take.
Okay. It's definitely taking like a long time to figure out. I guess I just haven't hit a point where I'm like, I have absolutely no idea what to do to try to figure it out.
Okay, yeah, so that's good. That's, that to me indicates an appropriate level of challenge. I don't want you to ever get to the point where you're like, I have no idea how to start this even. So if it gets to that point, then you should let me know, because that's probably too hard. Don't forget, I have office hours on Friday morning as well. And if you can't make those 9 to 10:30, just send me an email if you'd like to meet. Okay?
Thank you.
Yeah, I'll see you all on Friday.
There's two really quick questions about the homework actually.
Sure.
For the 1A, so 1A is about the which primitive roots, if you think, are